Our recent videos introduced the Fourier transform. I thought it'd be nice to visualize what was going on with some examples. So the first property that we discussed when introducing the Fourier transform was its relationship to the coefficients in the Fourier series. So here I have typed in a function, f of t. It's going to be the blue picture that is depicted, and overlaid on the blue graph, I have plotted the Fourier series for this function up to the 15th term. So sines and cosines up to cosine 15 pi and sine 15 pi x. We've seen this example before. The gold function approximates the blue function, and the larger I increase the number of terms, the better the approximation. So I would actually like to show you explicitly what the first few terms in the complex form of the Fourier series is. The complex form of the Fourier series has exponential functions times some coefficients. So here I have an exponential function e to the 2it times a coefficient, e to the negative 2it times a coefficient. Here's the coefficient of e to the it and the coefficient of e to the 0t. I can make a table containing these coefficients. So here I'm going to show you a table containing the coefficients in this Fourier series where n can go from negative 12 to 12. So for example, the coefficient of e to the 2it should be this term highlighted, and I can see that term on my list here that corresponds with n equals 2. The n equals 0 term is pi over 16, so I could see the n equals 0 term is pi over 16 here. Apparently the coefficient in the Fourier series when I take e to the negative 12, since I'm plotting from negative 12 to 12, is I over 48. Okay, so I have this list of Fourier coefficients. I want to show you that I can get this same list from the Fourier transform. Okay, so first I'm going to plot this list. Now this list has complex numbers in it. Complex numbers have a real and an imaginary component. So the first thing I've plotted here is the real component of each number on this list. So for example, when n is negative 12, there is no real component. That's why this is a 0 here. If I'm at n equals 0, then I have the coefficient pi over 16, and that is this dot here. So I plotted all the real coefficients, and I can also extract the imaginary coefficients and plot that. So I've done that here. So I have the plot of the real part of the coefficients in the Fourier series and the imaginary component of the coefficient in the Fourier series. Okay, well, now let's look at the Fourier transform. So I have typed in here the Fourier transform as we've defined it. So we've defined the Fourier transform to be this integral transformation, and I typed that in, entered it, and I got this as the result. So I'm going to extract the real part. The real part involves this first term and the cosine term. I'm going to look at the real part, and I'm going to plot that on the same graph as my real plot of the coefficients of the series. So let's see here. And you could definitely see that the Fourier transform, the real component, is a continuous function that evaluates at the integers to the coefficients in my Fourier series. So you can see that the continuous function goes through the points in my plot. And the same thing should go for the imaginary component. Yes, so the imaginary component of the Fourier transform is the continuous function that matches what I would expect with its relationship to the coefficients in the Fourier series. Okay, so that's the relationship between the Fourier series coefficients and the Fourier transform. A key property that we've seen are the Fourier relations. So the Fourier relations I'd like to visualize here. Now, the Fourier relations say that if I do this integral, which I'm highlighting now, That's the integral of my Fourier transform times e to the positive I omega t. And if I integrate with respect to omega, I should get back my original function. So I didn't want to do the integral from negative infinity to infinity, so I typed in the integral from negative 20 to 20 just to get a good approximation. I did that calculation, and I will plot my original function along with this approximation. So you could see that the gold function is again a good approximation of the blue function f of x, now, or f of t. Now, this gold function is a different approximation we got from the Fourier series. So back before, this was our graph of the Fourier series. The new picture that I have is actually a little bit different. It looks very similar, but it's a little bit different. And furthermore, this new picture has a property that the old Fourier series approximation did not have. Here, watch this. So if I go back to my Fourier series, this is the Fourier series picture, I get a good approximation of my function on the interval from negative pi to pi. But as we've seen in a previous video, if I increase that interval, let's say from negative 5 pi to 5 pi, I get a bad approximation of my function off of the interval that I'm interested in. I just get a repeating graph. This graph repeats itself 5 times because I've repeated the interval from negative pi to pi 5 times. If I go now to the approximation from the Fourier transform, and I plot that graph on the interval from negative 5 to 5 pi, I should not see the same thing. My approximation is still good over the entire real line. So I don't have this same sort of periodic feature I see in the Fourier series. So the Fourier transform is a little bit better there. So this is a visual representation that if I apply the Fourier relation, I get back my original function. All right, now finally in this video, I'd like to visualize what we did in the previous video by solving the heat equation with the Fourier transform. So we did solve this heat equation. We're thinking about a rod of infinite length, and at time 0, it's struck by lightning. That's modeled by this Dirac delta function. So we solved it and we got this solution in the previous video. So let's see what happens if I plot this. So I'm going to plot this for different times t in an animation. So this is a time close to 0. I started t at time 0.01. I didn't start time at exactly 0 because at that moment in time, the lightning hits the rod and it's infinitely hot for 1 nanosecond. And I get a spike in the graph, and Mathematica, the software, doesn't like plotting an infinitely tall picture. So I started at time 0.01. So let's see what happens if I plot various values of t and x for this function. You could definitely see that as time goes forward, the heat diffuses throughout the medium very rapidly, very rapidly. So at time 0, I hit by lightning now, and it goes, the heat travels throughout the whole rod. Okay, so those were some visualizations of our recent videos on the Fourier transform. Wonderful.